Akhil Potla is he was a petroleum engineer undergrad, but he's actually getting a master's in engineering mechanics, and I supervise him. He's working on implementing this CRM capacitive resistance model as a scikit-learn estimator. So he's going to show us some progress to date on that.
All right, can everybody see the screen?
We can see it.
All right, guys, so I'm going to talk about how we chose to implement CRM as a scikit-learn estimator and why we chose to do so. So we chose to implement CRM as a scikit-learn estimator because scikit-learn provides us a lot of cross-validation tools along with other data science tools that we could take advantage of if we implemented it in the common API that scikit-learn provides us. And like people have said earlier, scikit-learn is the most popular machine learning library in the world. And then from an oil and gas perspective, the goal is to use CRM and machine learning techniques to predict the oil production rate and to optimize the injection rate. And so we're using CRM to predict the production rate. So first, we're going to quickly discuss the origins of CRM. CRM was first proposed in 1943, so it is quite an old model. And it was first proposed by Bruce. And so what they chose to do is, much like how we divide reservoirs into grid blocks for other purposes today, they did the same thing. And so here we have a reservoir grid block unit. And on the left, we have the inputs, and on the right, we have the outputs. We have an input pressure and an input flow rate. And on the right, we have an output pressure and an output flow rate. But then what they chose to do was they decided to use an electrical analogy to model flow rate. So they built an actual physical machine similar to the schematic below. And so here, the capacitors would represent the reservoir unit storage capacity of each of the grid blocks. And then the resistors are the inverse of transmissibility. And so the particular form of CRM that we're looking at today is going to be the producer volume version. Here we have a producer well. As you can see, it's this green vertical line. Then it's associated with the volume. This green circle represents that volume. It is the volume that this producer produces from. And then we have 6 injector wells in this example. And so there are 2 variables that we try to fit each well to. It is tau, which is the time constant. And then the F values are the gains. And I'll discuss these a bit more in a couple slides. But first, CRM makes some assumptions. The reservoir needs to be in constant pressure, or excuse me, constant temperature. The fluid should only be slightly compressible. There should not be any formation gas. There are negligible capillary pressure effects, and the reservoir itself is in constant volume. So discussing the time constant, you can see that it is the total compressibility times the pore volume over the productivity index. And that gives us a time constant in days, the time it takes for fluid to go from the injectors to the producers within that particular volume. And then we have the gains. So the gains are the fraction of the increased production rate contributed by a particular injector. So basically, it is the production rate at producer J contributed by injector I over the total injection rate. And so that should give us a fraction. And then the sum of all the gains for all the injectors should be less than or equal to 1. And this is the actual CRM equation. Here we have the production rate at producer J at time step K. And then this variable here is the change in time, with each time step. And so this is a decline term plus an increase in production rate caused by the injection of fluid. And then that gives us a flow rate in barrels per day. So first, we validated our model using synthetic data to ensure accuracy and correctness. So we have some synthetic data with 4 producers and 2 injectors. And CRM was used to develop this data. And then the goal is to ensure that CRM can predict or can match the true values of the parameters across the parameter space, because CRM is a linear model with a convex objective function. So here we're just looking at the first producer, and actually I'll back up once. It is this blue line right here. It is a bit hard to see with all the other producers. And so here we have our parameter space. All the green dots represent various initial guesses that we've tried across the parameter space. And the red X's are the final values. So once we pass the model that initial guess, and then we fit the data, we see that it all goes towards the true value. And this is what we'd expect for a linear and convex model. And then you can see that all the initial guesses overlay on top of the data as CRM was used to develop the data. So, and on the left half, we see that the model accurately predicts, or excuse me, accurately fits the data. And then we can see that on the right-hand side, it accurately predicts the data. And now we use real data. So this is real data from a well that we have. And you can see that we have production data over the course of about 4 years, and that the production rates are pretty high. And so we do the same thing here, except I don't have a nice graph to show you since this is a higher dimensional parameter space, as there are more injectors. But we can see that on the left-hand side that we use to fit the data, CRM does a fairly good job of fitting the data. And then on the right-hand side, it does a fairly good job of predicting the data. Oh, one discussion is you can see sometimes there are smaller periods of shut-in, and we do not predict the data as well in the shut-in periods, but that is expected. One of the primary goal of this project was to have a very usable scikit-learn estimator for our CRM model. So first, I'm going to actually show us an example using linear regression. So here we can see that we've just import our linear regression model from scikit-learn. Then we can initialize the model and then fit it using the training, feature matrix, and the target vector. And then here we have our coefficients, which are the parameters that the linear regression model chooses to fit, printed out here. And then you can see the prediction on the testing data. And that's actually the plot that I have below here. It is the second half of the data. So you can see the dark blue is the actual, and the light red is the prediction. And I've omitted the construction of the feature matrix here because of space, and omitted the plotting code. And so here's an example with CRM. You can see that it is the exact same API. We import, we fit, and then we predict. And here we have our feature matrix, the output for our variables, and then the predict. And then on the bottom, we have a plot here. You can see that CRM does a better job than linear regression at predicting the data, and that's to be expected since CRM is an actual physics-based model. And in the future, we want to analyze the oil cut. And then this gives us a lot of different opportunities. We can use more physics-based models such as COBOL. We can use machine learning estimators or deep learning, a whole bunch of other techniques. And then we also need to investigate the uncertainty of the models that we have. I'd like to thank our sponsors.
Thank you very much, Akhil. Appreciate your presentation. We have time for questions. Do we have any questions from anyone? John, I think this is the way of the future. Developing great code that people can easily deploy within their organizations through standard type of coding practices, right?
I hope so.
You know, code repeatability, how do we call it? Unit testing. Am I using the right terminology?
That's right. You can just say software engineering.
Software engineering. And that's important. People being able to use the results that we develop, I think we can go the next step, make things widely deployable.